Hello everyone! Welcome to the first lab explanation video in the How to Build and Train Your AI Model program, sponsored by my nonprofit InspiredK.org. Today we're going to be going through Lab 0, the Python Introduction tutorial, and a link for this lab can be found on my nonprofit's website, InspiredK.org. We're going to be running this lab on Google Colab, a virtual environment that requires no local resources, and you can run this lab on Google Colab as well. In Python's basics, we're going to be covering built-in types such as lists, tuples, and dictionaries, loops, and Python's libraries such as NumPy. First, I'd like to start with the built-in types, and more specifically, lists. We're going to start by building a list of 5 names, Zach, Jay, Richard, Abby, and Kevin, to build our understanding. Let's first start by creating the list of names with square brackets and each item separated by a comma and a space. We're going to start this list with the names Zach and Jay. Then we're going to access the first name in our list by using indexing. Indexing is a method of having each item inside of the list assigned to a specific number. So our first name, Zach, is at index 0, our second name is at index 1, and if we had more names, then they would be at index 2, 3, and so on. If we access the first name at index 0, we can use the print statement in order to see the output of this indexing in the console. So when we print this result, we see the name Zach because Zach is at index 0 in our names list. To add a new name to our list, we can use the .append method, and this will be used with names.append Richard because we want to add the name Richard. When we print our new list of names, we see that our list now contains 3 names, Zach, Jay, and Richard. If we want to find the length of this list, we can use the len method, which is used with len, open parentheses, names, close parentheses. If we print this length, we see 3 because we have 3 names, Zach, Jay, and Richard. Additionally, we can put 2 lists together by using the plus equals operator. Plus equals operator is equivalent to having the first list of names equal to that list plus the new list. It can also be used for other operations such as subtraction, multiplication, and division, as well as on different types of variables. So let's add the new list of names Abby and Kevin to our original list of names. This provides us with our final list of names containing the 5 names Zach, Jay, Richard, Abby, and Kevin. Now I'd like to take a look at some other different list examples. The first I'd like to look at is the 2 different ways to create an empty list. The first is using an empty pair of square brackets, and the second is using the list parentheses constructor. Both of these create the exact same list, but the first is useful if you want to quickly create a list, whereas the second is more useful if you want to remember that your variable is actually of the type list. Additionally, in Python, lists can contain different data types without having any issues. So for example, our list called stuff has the integer 1, an inner list containing hi and bye, the floating point number -0.12, and the null value none. If we attempt to print this list, we see it comes without any errors because Python has support for these different data types. So far we've covered the different ways to manipulate lists, including defining them, indexing, which accesses specific parts of the list, appending and adding names, finding the length of our list, and concatenating 2 different lists together, as well as the 2 different ways to define a list and how different data types can be included in a list. Now, I'd like to cover list slicing, which is one way to change lists that accesses specific elements or specific parts inside of a list. So first, for example, let's initialize a list called numbers that contains the integers from 0 to 6. So that's going to be 0, 1, 2, 3, 4, 5, and 6. Let's say I want to get the first 3 numbers in this list, so I'm going to use the syntax numbers, open square brackets, 0, colon, 3, close square brackets. The 0 is our given start index for our slicing operation, which is included, and the 3 is our ending index, which is exclusive. This means that an item at index 0 will be included, while the item 3 at index the ending index 3 will not be included. So when we run this code, we see that 0, 1, and 2 were outputted, as those are the first 3 items at index 0, 1, and 2. The reason that 3 is not outputted is because our third index is not included, exclusive. When we don't specify a starting index, it is assumed to be the start of our list. So if we use :3, we're going to see the same output as before, as that starting index is assumed to be the 0th index. So we have 0, 1, and 2. When an ending index is not specified, it is assumed to be the end of our list. And in this case, it would be 7, as that 7th index is not included, and the maximum index we have is 6. So if we have 5 : we're going to see the numbers 5 and 6 outputted, as at index 5 we have the number 5. Until the end of the list, the only remaining number is 6. Something special about Python is that if you don't define a starting or ending index, the entire list is taken as a copy in the memory, which will be very useful later in NumPy when we want to take copies of the entire list and only edit that new copy without changing the original list. When we use the not start defining the starting or ending index, we can see that we get 0, 1, 2, 3, 4, 5, and 6, our original list. Something else that's unique about Python is that negative indices can be used to define numbers or items that could be from the end forward instead of the starting forward. So if we access the item at -1 index, we're going to have the end of the list and that first item at the end. So as we can see, we get the item 6, as that is the last item at index -1. We can also use negative indices for slicing in the same way as positive indices, but instead of from the start to the end, we go from the end to the start. So if we start by having the -3 index till the end, we will be from the third last index to the end of the list. So if we count from the back, -1, -2, -3. So at our -3 index, we have the number 4. So that slicing operation is going to have 4, 5, and 6. Additionally, the slicing operation from 3 to -2 will go from our third index item to our second to last item. So let's find the item at index 3. 0, 1, 2, 3. So the number 3 is at our third index. The second to last item, we can count from the back. -1, -2. So as we can see, that second last item is 5. But because the ending index of a slicing operation is not included, so our starting index is from 3, and then our ending index is from -2, we're only going to see the integers 3 and 4, as 5 is not included. So when we run these two operations, the first operation did indeed output 4, 5, and 6, and the second operation, 3 to -2, did indeed output 3 and 4. In summary, we covered how we can slice lists by first defining an example list, showing how positive indices can be used for list slicing, and how copies can be taken without defining a starting or ending index. Furthermore, we saw how negative indices can be used to slice lists from the end to the start. Next, I would like to cover tuples. Tuples are extremely similar to lists, but unlike lists, they cannot be changed. This means we cannot add elements, remove elements, or slice a tuple. So first, let's define a tuple with the exact same method with lists, except instead of square brackets, we're going to have parentheses. So let's define a names tuple containing the names Zach and Jay. Similar to lists, we can access an element in this tuple by using indexing. So if we want the name at index 0, we will get Zach because that's at index 0. We can also find the the tuple length at length with the len operator, and when we run both of these lines, we see that the name at index 0 is Zach, and the length of our tuple is 2, as we have 2 names so far, Zach and Jay. However, we cannot reassign our item at index 0 to a new value. So if we attempt to change Zach to Richard, because it is at index 0, this will not work because tuples do not support item assignment. This means that we cannot change any of the items in our tuple once we already defined it. Now I'd also like to have some other tuple examples, including the second way to define a empty tuple with the tuple parentheses constructor. This creates the exact same tuple as the closed parentheses, but is similar to the list definition. It is helpful if you want to remember that the variable you are defining is a tuple. Additionally, special syntax is needed to create a tuple that has one single item. So if we want to create a single tuple with the item 10 in it, we have to put a comma after this integer in order to ensure that it is defined as a tuple. So when we run this code block, we can see that our tuple constructor outputs an empty tuple with empty parentheses, and the single tuple is defined as a tuple with 10 and a comma after it. So in summary, we saw how tuples are similar to lists, but they do not support changes into their items, and we cannot have any item reassignment as well. Additionally, we saw how to create empty tuples in two different ways, as well as how to create a single item tuple. Now, I'd like to cover dictionaries, which are lists of different mappings between keys and values. They are especially useful in AI when we need to map characters to indices or indices to characters. The two ways to initialize an empty dictionary are with curly brackets or with the dict constructor. Similar with lists and tuples, the dict constructor is used whenever you want to remember that your variable is a dictionary instead of any other type. If we want to create a dictionary that has one key value pair, we have to define it as a key, space, the value. So if we want to create a phone book dictionary, we open the curly brackets, say Zach is assigned to the phone number 12-37, and close the curly brackets. This example, we are pairing a string to a string, but many other data types can be used as well. If we want to add another item to our dictionary, we use a syntax of the name of the dictionary, phone book, open square brackets, J, close square brackets, equal to the phone number. So now with this code, we're going to add J as the key and the respective value of 34-23 as the phone number. If we want to check if there's a key inside of our dictionary before referencing the key in further code, we can avoid errors caused by checking if that key is in our phone book by using the syntax of key in phone book. So for example, if we want to check if Zach is in our phone book, we use Zach in phone book. If we want to check if Kevin is in our phone book, we use Kevin in phone book. These operations will return either a true or false value, as Zach is in our phone book, so that is true, as he is one of the first keys, and Kevin is not in our phone book, returning a value of false, as he is not found in the dictionary. If we want to get the corresponding value for a key in the dictionary, we can do this by calling the key from inside of it. So we use the syntax, the name of the dictionary, open square brackets, J, close square brackets, to get J's phone number. When we print this, we see 34-23 is outputted, as that is the respective phone number for J. If we want to delete a key value pair from a dictionary, we can use the del keyword, as well as the name of the dictionary and which key we want to delete, as well as its variable, or its value. So if we want to delete Zach and his phone number, we can use the del phone book Zach syntax, and when we print our final phone book, we see that only J is left with the phone number 34-23 assigned. So far we have covered how dictionaries can be defined with empty or with one item, how to add items to the dictionary, how to check if there are items in the dictionary, how to get the value for a given key in the dictionary, and how to delete key value pairs. Now I'd like to cover loops, which are a way in Python to loop through and iterate over different data types. The two different loops in Python are for and while loops, and although they are both very important, for loops are usually more commonly used in AI. So to define a for loop, we use the syntax of for the variable in a list. And then inside of that, we use an indentation with spaces in order to indicate whatever is inside of our loop. So for example, if we want to print each of the integers in a range from 0 to 5, with 5 being excluded, we can use for I in range of 5, and the range constructor creates an automatic list containing the integers 0, 1, 2, 3, and 4. For each I in that list, we can print it on a new line. When we run this code, we see that 0, 1, 2, 3, and 4 are outputted independently of each other, which is how the loop works. If we want to loop through a list, we can use an example list. Let's make it with different names. So let's start with Zach, Jay, and Richard. And we can use the similar syntax as before with for name and names and print each name independently. If we do this, we can see that Zach, Jay, and Richard are printed in the order that we define them in, each on their own line, as they are independent. To iterate over the values in a list as well as their respective indices, we can use two different methods. First, we can loop through a range of the length of the names list, so from 0 to the length with the length being excluded, and then get each item for each respective index. So if we use this with for I in the range of the length of the names list and print each index with its respective value, we can see that 0 is Zach, 1 is Jay, and 2 is Richard. The second method that we can use is called enumerate, which takes the list and automatically assigns an index to each value. This uses special syntax as each item has two different values for it. So we can use for I, name in enumerate of names and print each index and its respective name. When we do this, we see the exact same output as before, with the 0 index with Zach, 1 with Jay, and 2 with Richard. So far, we have covered how for loops work and how we can loop through lists. Now I'd like to show how we can loop through dictionaries. So first, let's define a phone book dictionary with the keys Zach and Jay and the phone numbers 12-37 and 34-23 respectively. To iterate over these keys, we can use two different methods. First, we can use the same format as a loop for a list and have for name in phone book and print each name, or we can use the .keys method in order to only loop through the keys. So as you can see, both of these loops return the same output, Zach and Jay, but the .keys method is more useful if you want to make sure that you are only looping through the keys in a dictionary. If we want to iterate only over the values, we can use the .values method similar to .keys, and for each number in the phone book values, we can print it and see that 12-37 and 34-23 are returned respectively. To iterate over the both key and value pairs in a dictionary, we can use similar syntax to the values and enumerate methods. We take the .items method and we use the name, space number, as each item in the .items will have a key and value, two different values. If we print each name with its respective number, we can see that Zach has a phone number of 12-37 and Jay has a phone number of 34-23. So now we have covered how to loop through dictionaries with for loops. Now I'd like to cover Python libraries, and more specifically NumPy. NumPy adds Python support for large multi-dimensional arrays, as well as optimized and high-efficiency operations on these arrays. So first, let's import NumPy using the syntax import NumPy as np. The as np part is not necessary, but we're going to import it as np as we're going to use this name a lot in the future, and it is easier to remember and achieves cleaner code. Now let's look at NumPy arrays, which are the main data type used in NumPy. They're similar to lists, but they now support multiple dimensions as well as faster operations built into NumPy. Let's define three different NumPy arrays to see how they work. First, we're going to define a one-dimensional NumPy array with the items 1, 2, and 3. Next, we're going to define a NumPy array that is now two-dimensional but still contains a one-dimensional input, 3, 4, and 5. Finally, the third array is now two-dimensional with the shape 2 by 2, and it has the entries 6, 7, 8, 9. If we use the .shape method on our first two arrays, we can see that the shapes of these NumPy arrays are defined as tuples, with the first array having a shape of 3 as it is one-dimensional, while the second array has a shape of 1 by 3 as it is two-dimensional, but the second dimension only has one entry. Additionally, we can see the last array has a dimensionality of 2 by 2, as it has 2 rows by 2 columns, 6, 7, 8, 9. Now, before we go any further, I'd like to define a couple of key terms. First, vectors, which are one-dimensional arrays with a shape of n, or two-dimensional arrays with a shape of n by 1 or 1 by n. Although these shapes are all not exactly identical, they are all still vectors. And as we can see, the first two arrays we defined are shape 3 and 1 by 3, making them vectors. Matrices, on the other hand, are two-dimensional arrays or more, usually with shape m by n, and the last array that we defined has a shape of 2 by 2, making it a matrix. I'm going to be referring to one-dimensional arrays as vectors and two-dimensional or more arrays as matrices. Before we move on, I'd also like to show how we can reshape different NumPy arrays using the .reshape method. So first, let's define an example array using the NumPy.aRange method to find all of the integers from 0 to 10, with 10 being excluded, and create a NumPy array with them. So when we run this code, we can see that the NumPy array contains 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Then we can use the .reshape method with a shape of 5 by 2 in order to give this NumPy array 5 rows by 2 columns. When we run this, we can see that now we have 5 rows and 2 columns with the entries 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 5 rows with 2 entries each. So far, we've covered how NumPy arrays are defined, the .shape method to find the shape of NumPy arrays, as well as how we can reshape NumPy arrays to different shapes as long as we need them. Next, there are several different array operations that can be used on NumPy arrays. And first, I'd like to go through the np.max method. First, let's define a toy NumPy array with shape 3 by 2 that contains the entries 1, 2, 3, 4, 5, 6. When we print this array, we see it has 3 rows and 2 columns with the entries 1, 2, 3, 4, 5, 6. And its shape is indeed 3 by 2. Now let's use the np.max method to get the highest number in each row or column. We can choose if we want to find row or column maximums by defining the axis parameter. If axis is equal to 0, then we are going to find the max in each of the columns, whereas if axis is equal to 1, then we find the maximum in each of the rows. Let's use axis equal to 1, and when we run this, we will see a one-dimensional NumPy array with the entries 2, 4, and 6. This is because in each of the rows, 2 is greater than 1, 4 is greater than 3, and 6 is greater than 5. This new array does not actually need a second dimension, since each row was summarized into its own value. This gives the new max array a shape of 3. However, if we want to maintain the second dimension, we can use the keepDims parameter and set it to true. This will give a second dimensionality to our maximum array, as well as a 3 by 1 shape. So now it is still a vector, but it still has 2 dimensions. So far, we have covered the np.max method, as well as defining a NumPy array and using different NumPy.max methods to see how it works. Now let's look at different matrix operations that are defined in NumPy. So first, let's define 2 different NumPy arrays, the first having a shape of 2 by 2 with 1, 2, 3, 4, and the second array having a shape of 2 by 2 with 3, 3, 3, 3. When we print these arrays, we can see that they do have a shape of 2 by 2 each, and they are 1, 2, 3, 4 in the first matrix, and 3, 3, 3, 3 in the second. Now let's perform an element-wise product where each of the corresponding elements in each matrix are multiplied. We can see that we can do this with the asterisk operator, and we have the now 2 by 2 array 3, 6, 9, 12. This is because 1 times 3 is 3, 2 times 3 is 6, 3 times 3 is 9, and 4 times 3 is 12. The dot product is another way to manipulate matrices, but it's usually more commonly used for vectors. So the dot product multiplies each of the corresponding elements in each vector, and it sums all of those products to reach a final answer. Let's define 2 more NumPy arrays, one with the entries 1, 2, and 3, and the second with the entries 1, 10, and 100. Each of these vectors are one-dimensional with shape 3. So now let's use the np.dot method to perform dot product on both of these vectors. So first, we're going to see how this dot product will calculate 1 times 1, which is 1, 2 times 10, which is 20, and 3 times 100, which is 300. 1 plus 20 plus 300 is 321. when we run this code, we see that 321 is indeed outputted. Additionally, we can use u.v in order to perform dot product on the first vector u and the second vector v. This still returns 321. Now let's try the dot product on two different arrays that have different dimensions. Let's define a new array called w that is a shape of 3 by 2. So it's going to have the entries 1, 2, 3, 4, 5, 6. Also, let's work with the v vector from before that has the entries 1, 10, and 100. When we look at both of these vectors, we see that the original vector has 1, 10, and 100, as well as a shape of 3, and the matrix has shape 3 by 2 with 1, 2, 3, 4, 5, 6. Now let's take the dot product of the vector and matrix, and we see that a shape of 2 NumPy array is outputted. This is because the vector is changed from a horizontal vector to a vertical vector in order to be multiplied with the first column in our matrix, and 1 times 1 is 1, 3 times 10 is 30, and 5 times 100 is 500. So 500 plus 30 plus 1 is 531, the first entry in our NumPy array. This is again done for the second column in our matrix, and we see that 2 times 1 is 2, 4 times 10 is 40, and 6 times 100 is 600, leading us to 2 plus 40 plus 600, or 642, the second entry in our NumPy array with the dot product. Now let's try a different order for this dot product with the matrix by the vector. This does not work as the shapes 3 by 2 and 3 are not aligned. We can resolve this by using a method called transposition for the matrix. If we use this transposition, we can see that the w vector, which is shape 3 by 2, is changed to a 2 by 3 matrix, and the row 1, 2 is changed into the column 1, 2, the row 3, 4 is changed into the column 3, 4, and the row 5, 6 is changed into the column 5, 6. This leads us to the transposed vector of 1, 3, 5, 2, 4, 6. Now we can perform the dot product between the transposed matrix and the original vector and achieve the same output, as we can now multiply each entry in the vector by each corresponding row. So far we have covered how dot product works, as well as the element-wise product, and how dot product can be done between vectors with the same shape, as well as matrices and vectors with different shapes. Now, I'd like to cover the matrix multiplication, which is similar to the dot product, but it works with two different matrices and takes the dot product of each row in the first matrix and each column in the second. Then all of those dot products are combined to create a new matrix. Let's work with the A and B vectors from before, with shape 2 by 2, where the first one has 1, 2, 3, 4, the second one has 3, 3, 3, 3. When we perform the matrix multiplication, we can use the np.matmul method or the add operator, achieving the same result either way. So the reason we get this 2 by 2 matrix with 9, 9, 21, 21 is because the first row in our first matrix is multiplied by the first column in our second matrix. So 1, 2 is multiplied by 3, 3. So 1 times 3 is 3, and 2 times 3 is 6. So 3 plus 6 is 9, and the same is done for the first row and the second column. This is what gets us 9, 9 in our first row. Then the second row and first column are multiplied, 3, 4 times 3, 3, getting us to 3 times 3, 9, and 4 times 3, 12, and since 9 plus 12 is 21, we have 21 in the second row, as well as 21 in the last entry, because it is done the same for the second row and the second column. So now we covered matrix multiplication, which works with the dot product between two matrices. Now I'd like to cover indexing and slicing of different NumPy arrays, which is similar to the base built-in Python concept, but instead it now works with multiple dimensions. So first, let's define a NumPy array with random floating point numbers in the shape of 3 by 4. When we use the colon method, we select the entire NumPy array, which I detailed previously in lists. As we can see, this NumPy array has 3 by 4 shape with random floating point numbers inside of it. We can select the rows at index 0 and 2 by creating a new NumPy array with 0 and 2 inside of it, as well as selecting the entire row with the colon operator. And as we can see, we create a new NumPy array with 2 rows and 4 columns from the first and third rows of our original matrix. We can also select the second row at index 1 as its own vector, and then select its second and third items. We can do this by first having index 1 for the second row, and then the 1 through 3 selector, and since 3 is excluded, the items at index 1 and 2 in that row are chosen, which are the second and third items. As we can see, we get 0.791, etc., which is located here in the original matrix, and 0.697, etc., which is located here in the original matrix. Additionally, we can also use Boolean expressions in order to find all of the values that satisfy a given operation inside of our matrix. So if we want to check for all of the values that are greater than 0.5, we can use x is greater than 0.5, and we find that we have 10 different values that are greater than 0.5 in our generated matrix. Additionally, we can make our matrix 3D by using the np.new axis, as well as selecting all the rows and columns from the previous matrix. This gives it a shape of 3 by 4 by 1, which is illustrated when we add this new axis and we show it in the console. So now we have covered different matrix operations, as well as how we can slice and index NumPy arrays with multiple dimensions. Now I'd like to cover broadcasting in NumPy, which describes how it manipulates different arrays with different shapes in order to perform arithmetic operations on them. So when we are working with two different NumPy arrays, NumPy compares their shapes element-wise by starting from the rightmost direction towards the left. Two dimensions will be compatible when they are equal or one of them is equal to 1. So first, let's define 3 different NumPy arrays with random floating point numbers. So the first one will be shape 3 by 4, the second shape 3 by 1, and the last 1 by 4. We're going to see that these last 2 arrays are going to be broadcasted to match the shape of the first. So first, let's add the first and second NumPy arrays, and we will see that I forgot to run the first block. So we can see that the first array shape is 3 by 4, and the second array shape is 3 by 1. Our broadcasted result is shape 3 by 4 because the vector shape 3 by 1 is broadcasted across each of the rows in our original matrix. And so if we have the 3 by 4 shape, the 3 is going to be first done for the first column, then the second column, then the third column, and finally the fourth column. Another example would be multiplying the first matrix and the third vector with element-wise product. We can see that we have shape 3, 4 for the first matrix and shape 1, 4 for the last vector, and we get a result with shape 3 by 4. This is because in our 3 by 4 matrix, the 1 by 4 vector is broadcasted across each of the rows. So the first row, then the second, and then the third. Let's visualize this further by initializing 2 new NumPy arrays. The first being all zeros in a shape of 3 by 3, and the second being a 3 by 1 vector with 1, 2, and 3. If we print both of these arrays, we can see that the first matrix is shape 3 by 3 with all zeros, and the second is shape 3 by 1 with 1, 2, and 3. When we add these two arrays together, we get a 3 by 3 matrix, as the original 1, 2, 3 vector is broadcasted across each of the rows in our 0 matrix to achieve 1, 2, 3, 1, 2, 3, 1, 2, 3. So first, we have covered the basics of broadcasting by defining several different random floating point NumPy arrays with different shapes, and performing several operations on them to see how the broadcasting works, as well as a more visual example. And now let's get into the depth of broadcasting. So let's add 3 more NumPy arrays. The first being shape 3 by 4, second shape 3 by 1, and the third being shape 3. When we print all of these, we see that the first is shape 3 by 4 with random floating point numbers, the second is shape 3 by 1 with more floating point numbers, and the last one shape 3 with more floating point numbers. So first, we're going to attempt to add the second matrix to its own transposition. And when we see this, the first second vector is shape 3 by 1, and its transposition is shape 1 by 3. When we perform this, we see that the vector outputted is shape 3 by 3, as the original vector is broadcasted across all of its rows in order to achieve our 3 by 3 vector with all of the values added. Next, let's try to add the first matrix to the second vector, and we see an error as the 3 by 4 and 3 NumPy arrays could not be correctly broadcasted. So we're going to see two different ways to resolve this issue. First, we can transpose A to switch its rows and columns to make it shape 4 by 3, and then transpose the result, giving us a NumPy array with shape 3 by 4 with no errors. And the second way is to add a new axis to the vector of shape 3 to make it shape 3 by 1, which also resolves this issue and achieves the same result as the first solution. Now let's try a final operation adding the two vectors, the second and the third, together. When we perform this operation, we see a NumPy array shape 3 by 3 as the broadcasting works together in order to achieve this result with correct addition and no issues. So far, we've covered more complex examples of broadcasting with 3 different examples of NumPy arrays containing random floating point integers as well as different dimensions, and we showed how transposition can sometimes affect these broadcasting operations. Finally, I'd like to show an example of how NumPy code is extremely more efficient than normal built-in Python loops. In fact, when using for loops, they can sometimes be 10 to 100 times slower than normal NumPy operations with NumPy arrays. So let's use the %% command built into Google Colab to see. We're going to use two different codes, the first with for loops and the second with NumPy arrays, to add 5 to every element in rows 100 to 1000 in a 1000 by 1000 NumPy array. If we run this for the first slow for loop, we see that 333 milliseconds were taken for each loop. Next, let's do the same with fast NumPy array operations, and although it is seeming to take a slower amount of time on the front, we will in fact see that in the console output, it takes 13.5 milliseconds per loop, drastically faster. Now, let's recap over the entire lab. We started by covering built-in types in Python, including lists, including how to define them, add to them, slice them, create empty lists, and much more. Then we covered tuples, which are lists that cannot be changed, and we saw how when we attempted to reassign items, it would not work. Then we looked into dictionaries, which are mappings between keys and values, and we saw how to add and remove key value pairs from our dictionaries. Then we looked into for loops and saw how we can create a for loop, as well as how we can loop through lists and loop through dictionaries. Then we looked at NumPy, including how NumPy arrays work, what vectors and matrices are, how NumPy arrays can be reshaped, the numpy.max method, the matrix operations including element-wise product, dot product, and matrix multiplication, as well as how to slice and index NumPy arrays. Then we looked at how broadcasting works in NumPy, which is used to change different array shapes to have correct mathematical operations, as well as how more in-depth examples with transposition and other errors can affect broadcasting. Finally, we saw how NumPy code is far more efficient than for loops built into Python. I highly encourage you to go through the lab on your own because it will give you a deeper understanding of how Python works as well as how it can be used in AI. Thank you for your time and consideration, and be sure to look for more AI videos explaining the labs as well as recorded lectures coming in the near future. Thank you!